Hello there. Welcome to Dreamtime Documentary. Imagine a world reborn from near extinction, where ferns sway under starry skies and ancient seas pulse with life. 252 million years ago, the great dying silenced Earth, but life fought back. What if Earth lost 90% of life, yet rose again? Picture a scorched world, volcanic ash fading, as ferns pierce the soil and ancient seas stir with life. The great dying nearly ended it all. Can you guess what saved it? Dive into this sleep journey to uncover the mystery. Close your eyes and let your mind drift to a world in turmoil, where the earth trembles, skies burn red, and life clings to fragile threads. 252 million years ago, the Permian-Triassic extinction, the great dying, swept away 90% of all species, leaving a scarred and silent planet. In South Africa's Karoo Basin, fossils of therapsids, mammal ancestors, lie buried in ash, their bones whispering of loss. China's Meishan rocks hold layers of ocean death, where trilobites and corals vanished. The air was thick with sulfur, the seas turned acid, the land cracked under heat. Yet, from this devastation, life stirred, resilient, persistent, a quiet promise of renewal. Welcome to Dreamtime Documentary, where Earth's ancient tales unfold in soothing tones, guiding you into a peaceful slumber. Tonight, we embark on a 6.5-hour journey through the greatest extinction, exploring what ended it, how life rebuilt, and what it teaches us. Settle in. Breathe deeply, and let the story cradle you. The Great Dying was Earth's darkest hour, a catastrophe unmatched in scale. Fossils in Australia's Bowen Basin show trilobites disappearing, their delicate shells entombed in volcanic sediment. In South America's Esquigualasto Formation, dicynodonts with tusked snouts fell silent, their bones preserved in red sandstone. The event unfolded over hundreds of thousands of years, a slow-motion disaster driven by a perfect storm of forces we'll unravel. Yet, this crisis birthed the Triassic, a time of recovery where new life, dinosaurs, mammals, reefs, emerged from the ashes. Fossils from Italy's Dolomites reveal microbial mats, the first signs of ocean healing, replacing lost corals. As you relax, picture a barren landscape, cracked earth under a crimson sky, a single fern frond pushing through dust, its green a beacon of hope. The scope of this extinction was staggering. 96% of marine species, 70% of terrestrial vertebrates gone. In the Paleontologic Ocean, brachiopods and ammonites, once carpeting Japan's seabeds, dissolved in acid waters, their absence marked in 2023 paleontological records. On land, Glossopteris forests, preserved in Brazil's coal beds, withered into deserts, their leaves fossilized in ash. Insects, rarely affected by extinctions, suffered, with cockroach wings vanishing from Russian deposits. The causes, volcanism, greenhouse gases, ocean collapse, created a deadly cascade. But the end of this crisis marked a turning point. Survivors, small and adaptable, carried life forward. Imagine a silent shore, empty of trilobites, littered with shells, the air heavy, yet a tiny creature scuttles, the spark of recovery glowing faintly. Geologically, the Permian was defined by Pangaea, a supercontinent ringed by the vast Paleontologic Ocean. The Siberian traps, spanning millions of square kilometers, erupted with relentless fury, their lava flows preserved in Russia's basalt layers. Carbon dioxide and methane, released in torrents, warmed the planet 10 degrees Celsius, per 2024 Nature Geoscience data. Sediments in Japan show ocean anoxia, starving marine life. Volcanic ash in Greenland's cores blocked sunlight, triggering acid rain and climate swings. These forces, tectonic, atmospheric, oceanic, conspired to end an era, Yet recovery began within the chaos. Picture a volcanic plain, molten rock glowing red, skies choked with ash, the ground trembling softly. But in a distant valley, a seed germinates, life refusing to yield. Before the crisis, the Permian was a vibrant world. Forests of Glossopteris trees, their broad leaves catching sunlight, dominated Gondwana, preserved in India's coal seams. Therapsids like Dimetrodon, with sail-like spines, stalked South Africa's plains, their fossils in Texas's red beds showing predatory grace. Oceans teemed with trilobites, brachiopods, and coral-like reefs, their shells and structures carpeting China's limestone and Oman's rocks. Insects buzzed through humid air, dragonfly ancestors with 2-foot wingspans preserved in Kansas deposits. This rich, diverse world faced sudden collapse, yet its remnants held the seeds of renewal. Picture a lush Permian forest, ferns swaying in a warm breeze, a therapsid moving under dappled light, the air alive with the hum of life. The first signs of recovery emerged slowly, almost imperceptibly. Volcanic activity waned, as 2024 Siberian core samples reveal, easing CO2 emissions. Oceans began to reoxygenate, with microfossils in China's Meishan beds showing algae blooms by 251 million years ago. Rock weathering, per 2025 geochemical studies, absorbed carbon, cooling the planet. Survivors like Lystrosaurus, small and adaptable, spread across Pangaea, their fossils in Antarctica showing rapid reproduction. These signs, waning volcanism, ocean recovery, survivor resilience, mark the turning point. Picture a shallow sea, green algae spreading like a blanket, a Lystrosaurus nibbling ferns on the shore, the air fresh with renewal. Today, the Great Dying offers lessons for our world. Climate change, with CO2 at 400 parts per million in 2025 per NOAA data, mirrors Permian warming. Siberian permafrost thawing, releasing methane as in 2023 satellite data, recalls ancient gas spikes. Fossils teach resilience. Lystrosaurus adapted, much like modern efforts to restore Australia's coral reefs amid acidification. Geoengineering, like 2025 carbon capture projects in Iceland, echoes ancient weathering. The past guides us, urging balance. Picture a modern lab, scientists studying ancient rocks, a green forest rising beyond, the Earth's lessons whispering hope. This journey through the Great Dying will explore its causes, impacts, and recovery, weaving a tapestry of loss and renewal. As we delve deeper, let these ancient whispers cradle you, the planet's story a soothing path to sleep. Volcanic fury of the Siberian traps. The eruptions begin. The Great Dying spark ignited in Siberia, where the Traps volcanoes erupted with cataclysmic force 252 million years ago. Covering an area larger than Western Europe, these volcanoes spewed lava for millennia, their basalt layers still visible in Russia's Tunguska Basin, per 2024 geological surveys. Each eruption released vast clouds of ash, preserved in Greenland's sedimentary cores, dimming the sun and triggering acid rain. Carbon dioxide poured into the atmosphere, warming the planet by up to 10 degrees Celsius, as isotopic data from 2023 confirms. Picture a scorched landscape, rivers of molten lava glowing red, the sky a haze of ash, the air heavy with sulfur, yet a faint breeze carries hope. These eruptions, relentless and prolonged, set the stage for catastrophe. Fossils in Canada's Arctic show marine life suffocating as oxygen levels dropped. The Siberian traps, unlike modern volcanoes, erupted continuously, their impact global, reshaping climate and oceans. As you drift, imagine the Earth trembling, its fiery pulse a distant echo, guiding you deeper into rest. Greenhouse gas cascade. The volcanoes unleashed a cascade of greenhouse gases. Carbon dioxide, trapped in Siberian basalt, raised atmospheric levels dramatically per 2025 geochemical studies. Methane, released from melting permafrost and seafloor clathrates, amplified warming, as evidenced by carbon isotopes in China's Meishan rocks. This greenhouse effect turned lush forests into deserts, with Brazil's Permian coal beds showing charred remains. Ocean temperatures soared, reducing oxygen solubility, starving marine life. Picture a stifling plain, heat shimmering, cracked earth stretching endlessly, a lone plant wilting under a red sky. This gas surge drove the planet to a tipping point, ecosystems collapsing under the strain. Yet, within this heat, the first seeds of recovery waited, life's resilience unbroken. As you relax, let the image of a warming world fade, its intensity softening into calm. Global climate disruption. The climate spiraled into chaos. Volcanic ash blocked sunlight, causing initial cooling, followed by runaway warming, per 2024 Nature Geoscience models. Acid rain, detected in Japan's sedimentary layers, eroded soils, killing vegetation. Sea levels fluctuated, with coastal fossils in Oman showing submerged reefs. Storms intensified, as evidenced by eroded sediment in Australia's Bowen Basin. Picture a stormy sky, rain hissing on hot rocks, waves crashing over barren shores, the air turbulent yet strangely soothing. This disruption reshaped Earth, but as volcanism slowed, stability returned. The planet's rhythms steadied, offering a path to recovery. As you drift, let the storm's energy dissolve, its chaos a gentle lullaby. Early signs of resilience, 584 words. Even amid the fury, life persisted. Small therapsids, like Lystrosaurus, survived in burrows, their fossils in South Africa's Karoo Basin showing adaptation to heat. Algae, preserved in China's microfossils, began recolonizing oceans. Weathering of volcanic rocks, per 2025 studies, started locking away carbon, cooling the climate. Picture a sheltered valley, a Lystrosaurus nibbling sparse ferns, algae blooming in a quiet pool, the air cooling softly. These early signs mark the beginning of the end of the crisis. Life's tenacity, etched in stone, offers a soothing reminder of endurance. As you rest, let the image of a recovering world guide you, its quiet strength a path to sleep. Ocean collapse and anoxia. As we drift deeper into the great dying, let your mind settle on the vast Pan-Thalassic Ocean, its once vibrant waters turning dark and silent. 252 million years ago, the Permian-Triassic extinction struck hardest beneath the waves, where 96% of marine life vanished. Fossils in Japan's Pan-Thalassic sediments reveal shells dissolving in acid waters, while Oman's reef structures crumbled into ghostly layers. The oceans, Earth's lifeblood, choked on anoxia, oxygen starvation, and acidification driven by volcanic fury and greenhouse gases. Yet, even in this collapse, whispers of recovery stirred, faint but persistent. Picture a barren sea, waves lapping a desolate shore, the water heavy with silence, yet a flicker of algae blooms in the depths. This chapter explores the ocean's collapse, its causes, and the first signs of life's return. From acidification to anoxic dead zones, we'll uncover the devastation and the survivors that carried hope. Let these ancient waters guide you, their rhythms a soothing path to rest. Acidification effects. The Pan-Thalassic Ocean, stretching across Earth's Permian globe, faced a deadly assault from acidification. Volcanic eruptions from the Siberian traps, documented in 2024 geological studies, pumped carbon dioxide into the atmosphere at unprecedented rates. This CO2 dissolved into seawater, forming carbonic acid, lowering pH levels, as evidenced by dissolved brachiopod shells in Japan's sedimentary layers. Coral-like reefs, preserved in Oman's limestone, disintegrated, their intricate structures reduced to rubble. Trilobites, with their calcite exoskeletons, vanished from Australia's Bowen Basin fossils, unable to withstand the acid surge. The ocean's chemistry shifted, a slow poison spreading through currents, choking ecosystems that thrived for millions of years. Picture a reef, once vibrant with sponges and fish, now a crumbling skeleton under a gray, acidic tide, the water hissing softly as it erodes life's foundations. This acidification was relentless, stripping the seas of their diversity. Yet, in sheltered pockets, some organisms endured, their resilience a quiet promise. As you relax, let the image of a fading reef soothe you, its silence a gentle nudge towards sleep. Anoxic dead zones. As acidification spread, oxygen vanished from the oceans, creating vast anoxic dead zones. The Siberian trap's greenhouse gases warmed the seas, reducing oxygen solubility, per 2023 oceanographic models. Sediments in China's Meishan beds show black shale layers, rich in sulfur, marking zones where marine life suffocated. Ammonites, once abundant in Italy's dolomite fossils, dwindled as oxygen-starved waters spread. Fish and cephalopods, preserved in Canada's Arctic sediments, floated lifeless in currents. These dead zones, stretching across the Pan-Thalassic Ocean, silenced ecosystems, leaving only bacteria that thrived without oxygen. Picture a dark ocean, its depths still and heavy, no fish darting, no coral swaying, just a faint shimmer of sulfur under a cloudy sky. These anoxic zones were a graveyard, but in their margins, life clung on, waiting for oxygen's return. As you drift, let the stillness of these waters envelop you, their quiet a soothing embrace. Marine ecosystem loss. The collapse of marine ecosystems was catastrophic. Fossils from Japan's Pan-Thalassic sediments reveal a 96% loss of species, from trilobites to brachiopods, per 2024 paleontological records. Reefs, once teeming with sponges and crinoids in Oman's rocks, became barren, replaced by microbial mats. Predatory nautiloids, found in Greenland's fossils, vanished, their spiral shells buried in sediment. Plankton, the ocean's foundation, plummeted, as microfossils in China's cores show, starving food webs. The seas, once a symphony of life, fell silent, their ecosystems reduced to shadows. Picture a desolate seafloor, empty shells scattered, waves above carrying no life, the horizon gray and unending. This loss reshaped the oceans, clearing space for new life. The silence held the seeds of recovery, a faint promise of renewal. As you rest, let the image of an empty sea guide you, its calm a path to dreams. Survivor adaptations. Amid the collapse, survivors emerged, their adaptations a testament to life's tenacity. Small mollusks, like chlorea, found in China's Meishan fossils, thrived in low-oxygen waters, their thin shells resisting acid. Microbial mats, preserved in Turkey's limestone, colonized barren seafloors, creating new ecosystems. Foraminifera, tiny protists in Japan's sediments, reproduced rapidly, stabilizing food chains. Some fish, with fossils in Canada's shale, survived in shallow, oxygenated pockets, their small size an advantage. Picture a shallow bay, green microbial mats spreading, a lone chlorea shell glinting in pale sunlight, a fish darting through murky water. These survivors, small but resilient, laid the foundation for recovery, their adaptations echoing in the Triassic's rebirth. As you drift into sleep, let the image of a reviving sea cradle you, its quiet strength a soothing lullaby. Terrestrial devastation. Now, let your mind drift to the land, where the great dying's wrath scorched the Earth's surface, turning vibrant forests into desolate wastes. 252 million years ago, the Permian-Triassic extinction devastated terrestrial ecosystems, claiming 70% of land vertebrates. In Brazil's coal beds, Glossopteris forests lie charred, their leaves fossilized in ash. South Africa's Karoo Basin holds the bones of therapsids, once mighty predators, now silent in stone. Volcanic heat, acid rain, and climate chaos transformed Pangaea's landscapes. Yet amid the ruins, life's resilience flickered. Picture a cracked plain, once lush with ferns, now dusted with ash, a lone seed sprouting under a crimson sky. This chapter explores the terrestrial devastation, from forest collapse to the survival of the fittest. Fossils and rocks tell a story of loss and endurance, guiding you gently into rest. Let the Earth's ancient landscapes cradle you, their whispers a soothing path to sleep. Forest loss. The Permian's lush forests, stretching across Pangaea's Gondwana, faced annihilation. Glossopteris trees, their broad leaves dominating India's coal seams, withered as volcanic ash from the Siberian traps blocked sunlight. Per 2024 geological studies, temperatures soared 10 degrees Celsius, as evidenced by isotopic data from Brazil's Permian coal beds, turning humid woodlands into deserts. Acid rain, detected in Australia's sedimentary layers, stripped soils of nutrients, killing ferns and cycads preserved in Argentina's shale. Entire ecosystems collapsed, their debris forming coal layers in South America. Picture a forest, once vibrant with green canopies, now a graveyard of charred trunks, ash falling softly, the air heavy with heat. This forest loss reshaped terrestrial habitats, leaving barren plains where life once thrived. Yet, in sheltered valleys, seeds waited for renewal. As you relax, let the image of a fading forest soothe you, its silence a gentle nudge toward dreams. Vertebrate decline. Land vertebrates suffered catastrophic losses. Therapsids, like the saber-toothed gorgonopsians in South Africa's Karoo Basin, vanished, their fossils showing populations crashing. Per 2023 paleontological records, dicynodonts, with tusked snouts, dwindled in Russia's sedimentary beds, their bones buried in red sandstone. Only small, adaptable species survived, like Lystrosaurus, its fossils scattered across Antarctica. Climate extremes, from volcanic warming to acid rain, decimated food sources, starving herbivores and predators alike. Picture a dusty plain, a gorgonopsian skeleton half-buried, the sky red with volcanic haze, the ground trembling faintly. This vertebrate decline cleared ecological niches, paving the way for new species. Survivors, burrowing and resilient, carried life forward. As you drift, let the image of a barren land envelop you, its quiet strength a soothing embrace. Insect impacts. Insects, typically resilient, faced rare devastation. Dragonfly ancestors with 2-foot wingspans, preserved in Kansas deposits, disappeared, their delicate wings fossilized in ash. Cockroaches, found in Russian sedimentary layers, suffered die-offs, a rarity for such adaptable creatures. Per 2024 entomological studies, volcanic ash and heat disrupted breeding, while acid rain poisoned soils, killing plant-based food sources. Beetles and other pollinators, once buzzing through Permian forests, left sparse fossils in China's shale. Picture a silent woodland, no hum of wings, ash-coating wilted plants, the air still and heavy. This insect collapse disrupted ecosystems, but a few hardy species endured, their resilience a spark of hope. As you rest, let the silence of this lost world guide you, its calm a path to sleep. Early survivors. Amid the devastation, survivors emerged, their adaptations a testament to life's tenacity. Lystrosaurus, a small therapsid, thrived in burrows, its fossils in South Africa's Karoo Basin showing rapid reproduction per 2025 paleobiology data. Seed ferns, preserved in Australia's sedimentary layers, clung to sheltered valleys, their spores resistant to heat. Small lizards, ancestors of archosaurs, scuttled through sparse vegetation, their fossils in India's red beds marking early resilience. These survivors, modest but determined, laid the foundation for recovery. Picture a cracked plane, a Lystrosaurus nibbling a tough fern, a seed sprouting in ash, the air cooling softly. These early survivors, with their burrowing habits and hardy seeds, sparked the Triassic's rebirth. As you drift into sleep, let the image of a reviving land cradle you, its quiet promise a soothing lullaby. Toxic metals and pollution. As we journey deeper into the great dying, let your mind drift to a world poisoned by its own breath, where rivers ran dark and life withered under a toxic veil. 252 million years ago, the Permian-Triassic extinction unleashed a deadly wave of toxic metals and pollution, driven by the Siberian trap's relentless eruptions. Mercury, sulfur, and other poisons seeped into waters and soils, as evidenced by core samples from China's Meishan beds. Greenland's sediments reveal ash-laden skies, while Australia's fossil layers hold the remnants of dying ecosystems. Yet, even in this toxic wasteland, life found a way, its resilience a faint whisper of hope. Picture a murky river, its surface shimmering with metallic sheen, fish floating lifeless, yet a small microbe pulses in the sediment. This chapter delves into the toxic metals and pollution that intensified the Great Dying, exploring their sources and the survivors that endured. Let these ancient scars guide you, their story a soothing path to rest. Mercury spikes. The Siberian trap's eruptions released torrents of mercury, a silent killer that poisoned Earth's ecosystems. Core samples from China's Meishan beds, analyzed in 2024, show mercury levels spiking 252 million years ago, far exceeding modern thresholds. This toxic metal, vaporized by volcanic heat, settled into oceans and soils, as seen in Greenland's sedimentary layers. Marine life, like brachiopods in Japan's panthalassic fossils, absorbed mercury, their shells weakening before dissolving in acid waters. On land, plants in Brazil's coal beds show stunted growth, their tissues laced with mercury. This poison disrupted reproduction and metabolism, accelerating the extinction's toll. Picture a barren shore, a river glinting with metallic sheen, fish drifting lifeless, the air heavy with a faint, bitter tang. Mercury's spread was relentless, seeping into every corner of Pangaea. Yet, in its shadow, some life forms adapted, their resilience a quiet spark. As you relax, let the image of a poisoned river soothe you, its stillness a gentle nudge towards sleep. Sulfur's role. Sulfur, another volcanic byproduct, choked the Earth's air and waters. The Siberian traps released sulfur dioxide, forming acid rain that eroded soils, as evidenced by etched sediments in Australia's Bowen Basin, per 2025 geological studies. In oceans, sulfur fueled anoxic zones, with black shale layers in China's Meishan beds showing bacterial blooms thriving in oxygen-starved waters. These blooms released hydrogen sulfide, poisoning marine life, as seen in the absence of fish fossils in Canada's Arctic sediments. On land, acid rain stripped forests, leaving charred Glossopteris remains in India's coal seams. Picture a dark sky, sulfurous clouds swirling, rain hissing on barren ground, the air sharp with a chemical bite. Sulfur's toxicity amplified the crisis, but as eruptions slowed, cleaner rains returned, hinting at recovery. As you drift, let the image of a sulfurous storm fade, its intensity softening into calm. Ecosystem poisoning. The combined effects of mercury, sulfur, and other pollutants devastated ecosystems. In the Pan-Thalassic Ocean, trilobites and ammonites, once abundant in Japan's fossils, succumbed to toxic waters, their shells absent in upper Permian layers, per 2024 paleontological records. On land, therapsids like gorgonopsians in South Africa's Karoo Basin show signs of heavy metal poisoning, their bones brittle in fossil beds. Plants, critical to food webs, withered under acid rain and metal contamination, as seen in Brazil's stunted fern fossils. Food chains collapsed, starving herbivores and predators alike. Picture a desolate plain, plants yellowed and brittle, a lone therapsid skeleton under a toxic haze, the ground cracked and lifeless. This poisoning reshaped the biosphere, clearing space for new life. The silence held the seeds of renewal, a faint promise of resilience. As you rest, let the image of a toxic land guide you, its calm a path to dreams. Resistant species. Amid the toxic onslaught, a few species endured, their adaptations a testament to life's tenacity. Microbial mats, preserved in Turkey's limestone, thrived in sulfur-rich waters, forming new seafloor ecosystems, per 2025 studies. Small mollusks like chlorea, found in China's Meishan fossils, resisted mercury with thin, resilient shells. On land, seed ferns in Australia's sedimentary layers survived with toxin-resistant spores, sprouting in sheltered valleys. Tiny lizards, ancestors of archosaurs, scuttled through contaminated soils, their fossils in India's red beds showing metabolic flexibility. Picture a murky pool, microbial mats pulsing green, a chlorea shell glinting, a seed fern sprouting in ash, the air cooling softly. These resistant species, small but determined, laid the foundation for recovery, their endurance a quiet spark. As you drift into sleep, let the image of a reviving world cradle you, its resilience a soothing lullaby. Survivors of the Great Dying. As we journey deeper into the Great Dying, let your mind drift to a scarred earth, where life clings to existence amid ash and ruin. 252 million years ago, the Permian-Triassic extinction claimed 90% of species, leaving a world of barren plains and silent seas. Yet, in this desolation, survivors emerged, small, resilient creatures and plants that defied the catastrophe. Fossils in Antarctica reveal Lystrosaurus, a tenacious therapsid, grazing on sparse ferns. China's Meishan beds show microbial mats pulsing in recovering oceans. These survivors, modest but unyielding, carried the spark of life forward. Picture a cracked plain, a Lystrosaurus nibbling a tough fern, a faint green bloom spreading in a shallow sea, the air soft with renewal. This chapter explores the survivors of the Great Dying, their traits, and the new roles they carved in a healing world. From burrowing therapsids to hardy plants, their story is one of resilience, guiding you gently into rest. Let these ancient pioneers cradle you, their whispers a soothing path to sleep. Lystrosaurus traits. Lystrosaurus, a pig-sized therapsid, became the Great Dying's unlikely hero. Fossils in South Africa's Karoo Basin, analyzed in 2025, show its dominance, with bones scattered across Antarctica, India, and China, indicating global spread. Its small size, about 1 meter long, and burrowing habits, inferred from fossilized tunnels, allowed it to escape extreme heat and toxic air. Lystrosaurus had a beak-like jaw, perfect for cropping tough ferns, as seen in toothless skulls from Russia's sedimentary beds. Its high reproductive rate, per 2024 paleobiology studies, enabled rapid population growth, filling empty niches. Picture a dusty valley, a Lystrosaurus emerging from a burrow, its beady eyes scanning for ferns, the ground cracked but cooling under a pale dawn. Lystrosaurus thrived where others failed, its adaptability a beacon of hope. Its burrows, preserved in Australia's red beds, shielded it from volcanic ash and acid rain. As you relax, let the image of this humble creature soothe you, its quiet grazing a gentle nudge toward dreams. Marine survivors. In the oceans, where 96% of life vanished, a few resilient species endured. Small mollusks like Karoo, found in China's Meishan fossils, survived with thin, acid-resistant shells, per 2024 paleontological records. Foraminifera, tiny protists in Japan's Pan-Thalassic sediments, reproduced rapidly, stabilizing food webs. Some fish, preserved in Canada's Arctic shale, clung to shallow, oxygenated bays, their small size reducing metabolic needs. Microbial mats, seen in Turkey's limestone, colonized barren seafloors, creating new ecosystems. Picture a shallow sea, green mats pulsing, a Karoo shell glinting in pale sunlight, a small fish darting through murky water. These marine survivors, though few, laid the foundation for ocean recovery, their resilience a quiet spark. As you drift, let the rhythm of ancient waves envelop you, their gentle pulse a soothing embrace. Plant resilience. On land, plants faced near total collapse, but some endured. Seed ferns, preserved in Australia's sedimentary layers, survived with heat-resistant spores, per 2025 botanical studies. Their small size and rapid germination allowed them to colonize barren soils, as seen in India's fossilized roots. Conifers, early ancestors in Argentina's shale, clung to sheltered valleys, their needle-like leaves resisting drought. Algae, found in China's freshwater deposits, thrived in toxic pools, forming green films. These plants, modest but tough, stabilized soils and fed survivors. Picture a cracked plain, a seed fern sprouting, its green fronds trembling in a cooling breeze, a conifer standing tall in a distant valley. These resilient plants sowed the seeds of recovery, their growth a promise of renewal. As you rest, let the image of a sprouting fern guide you, its quiet strength a path to sleep. Terrestrial pioneers. Beyond Lystrosaurus, other terrestrial pioneers emerged. Small lizards, ancestors of archosaurs, scuttled through sparse vegetation, their fossils in India's red beds showing metabolic flexibility, per 2024 studies. Early synapsids, like Thrinaxodon, found in South Africa's Karoo Basin, survived in burrows, their whiskers aiding nocturnal foraging. Insects, such as beetles in Russia's deposits, adapted to sparse plants, their small size aiding survival. These pioneers, agile and adaptable, colonized empty landscapes. Picture a barren slope, a Thrinaxodon sniffing the air, a beetle crawling on a fern, the sky clearing to reveal faint stars. These pioneers, though small, reshaped the land, their movements a spark of life. As you drift, let the image of a reviving plain soothe you, its calm a gentle lullaby. Ecological niches. The Great Dying's devastation cleared ecological niches, allowing survivors to thrive. Lystrosaurus filled herbivore roles, its fossils in Antarctica showing dense populations, per 2025 data. Chlorea and foraminifera rebuilt marine food webs, as seen in Japan's sediments. Seed ferns and conifers stabilized terrestrial ecosystems, their roots in Brazil's shale preventing erosion. Small predators, like early archosaurs, hunted insects, their fossils in China marking new food chains. These niches, forged in crisis, set the stage for the Triassic's diversity. Picture a young ecosystem, Lystrosaurus grazing, a fern forest spreading, a small lizard darting under a starry sky. These new niches, born from loss, heralded recovery, their balance a testament to life's endurance. As you sink into sleep, let the image of a reborn world cradle you, its resilience a soothing whisper. Terrestrial pioneers. Beyond Lystrosaurus, other terrestrial pioneers emerged. Small lizards, ancestors of archosaurs, scuttled through sparse vegetation, their fossils in India's red beds showing metabolic flexibility, per 2024 studies. Early synapsids, like Thrinaxodon, found in South Africa's Karoo Basin, survived in burrows, their whiskers aiding nocturnal foraging. Insects, such as beetles and rushes deposits, adapted to sparse plants, their small size aiding survival. These pioneers, agile and adaptable, colonized empty landscapes. Picture a barren slope, a Thrinaxodon sniffing the air, a beetle crawling on a fern, the sky clearing to reveal faint stars. These pioneers, though small, reshaped the land, their movements a spark of life. As you drift, let the image of a reviving plain soothe you, its calm a gentle lullaby. Ecological niches. The Great Dying's devastation cleared ecological niches, allowing survivors to thrive. Lystrosaurus filled herbivore roles, its fossils in Antarctica showing dense populations, per 2025 data. Chlorea and foraminifera rebuilt marine food webs, as seen in Japan's sediments. Seed ferns and conifers stabilized terrestrial ecosystems, their roots in Brazil's shale preventing erosion. Small predators, like early archosaurs, hunted insects, their fossils in China marking new food chains. These niches, forged in crisis, set the stage for the Triassic's diversity. Picture a young ecosystem, Lystrosaurus grazing, a fern forest spreading, a small lizard darting under a starry sky. These new niches, born from loss, heralded recovery, their balance a testament to life's endurance. As you sink into sleep, let the image of a reborn world cradle you, its resilience a soothing whisper. Waning volcanism. As we drift further into the Great Dying, let your mind settle on a world where the Earth's fiery wrath begins to fade, the roar of volcanoes softening to a whisper. 252 million years ago, the Permian-Triassic extinction was fueled by the Siberian trap's relentless eruptions, but their decline marked a turning point. Core samples from Russia's Tunguska Basin, studied in 2024, show lava flows slowing, while Greenland's sediments reveal thinning ash layers. The skies, once choked with sulfur and ash, began to clear, allowing life to stir in the silence. Fossils in South Africa's Karoo Basin show Lystrosaurus grazing on new ferns, a sign of hope amid cooling lands. Picture a volcanic plain, its molten rivers hardening, a faint green sprout piercing the ash, the air cooling under a pale dawn. This chapter explores the waning of volcanism, a critical step in ending the Great Dying. From slowing eruptions to stabilizing climates, we'll uncover how the Earth began to heal. Let these ancient landscapes cradle you, their quiet recovery a soothing path to sleep. Eruption slowdown. The Siberian traps, spanning millions of square kilometers, drove the great dying with millennia of eruptions, but their slowdown was a lifeline for Earth. Geological core samples from Russia's Tunguska Basin, analyzed in 2024, show basalt layers thinning by 251 million years ago, indicating reduced volcanic activity. Each eruption had pumped out carbon dioxide and sulfur, warming the planet by 10 degrees Celsius, per 2023 isotopic studies. As eruptions waned, lava flows hardened, preserved in Siberia's rocky plains. This decline eased the greenhouse effect, allowing temperatures to stabilize. Fossils in Australia's Bowen Basin show early ferns sprouting in cooling soils, a sign of recovery. Picture a vast volcanic field, molten rivers slowing to a trickle, ash settling gently, a faint breeze carrying the scent of renewal. The slowing eruptions marked a shift, the Earth's fiery pulse calming. Life, battered by heat, found space to breathe. As you relax, let the image of a cooling lava field soothe you. Its quiet, a gentle nudge toward dreams. Ash reduction. Volcanic ash, once blanketing the skies, began to settle, clearing the way for recovery. Sedimentary cores from Greenland, studied in 2025, show ash layers thinning, signaling fewer eruptions. This ash had blocked sunlight, cooling the planet initially, then amplifying warming as greenhouse gases took over, per 2024 Nature Geoscience models. As ashfall decreased, sunlight returned, warming soils gently. Fossils in India's coal seams reveal seed ferns sprouting in clearer air, their spores surviving acid rain. Acid rain itself lessened, as sulfur emissions dropped, preserving soils in Brazil's sedimentary layers. Picture a sky, once dark with ash, now streaked with pale blue, sunlight filtering through, a fern frond unfurling in soft light. This ash reduction allowed ecosystems to stabilize, a critical step toward healing. As you drift, let the image of a clearing sky envelop you, its calm a soothing embrace. Climate stabilization. With volcanism waning, Earth's climate began to stabilize. The greenhouse effect, driven by carbon dioxide and methane, had raised temperatures 10 degrees Celsius, per 2024 isotopic data. As eruptions slowed, CO2 emissions dropped, and rock weathering, evidenced in China's limestone, absorbed excess carbon. This cooled the planet, as seen in Antarctica's fossil soils showing fern growth. Storms, once violent due to extreme heat, calmed, with Australia's sedimentary layers showing reduced erosion. Sea levels steadied, preserving coastal ecosystems in Oman's rocks. Picture a barren plain, clouds parting, a cool breeze stirring sparse ferns, the horizon softening under a pale sky. This stabilization gave survivors a foothold, their growth a sign of hope. As you rest, let the image of a cooling world guide you, its balance a path to sleep. Carbon cycle recovery. The carbon cycle, disrupted by volcanic CO2, began to recover as eruptions waned. Geochemical studies from 2025 show silicate weathering in Siberia's rocks locking away carbon, reducing atmospheric CO2. This process, seen in China's Meishan beds, cooled the planet, stabilizing ecosystems. Algae blooms, preserved in Japan's microfossils, absorb CO2 in oceans, aiding reoxygenation. On land, seed ferns in Brazil's shale sequestered carbon through photosynthesis, their roots stabilizing soils. These processes rebuilt the carbon balance, a slow but steady healing. Picture a shallow sea, algae pulsing green, ferns spreading on a cooling plain, the air fresh with renewal. This carbon cycle recovery was a cornerstone of the Earth's healing, paving the way for new life. As you drift, let the rhythm of ancient seas soothe you, their balance a gentle lullaby. Early ecological impacts. The waning volcanism sparked early ecological recovery. Fossils in South Africa's Karoo Basin show Lystrosaurus populations growing, their grazing supporting new food webs. In oceans, microbial mats in Turkey's limestone expanded, creating habitats for mollusks like chlorea, per 2024 records. Seed ferns and conifers, preserved in Argentina's shale, stabilized soils, enabling small lizards to thrive, as seen in India's fossils. These early ecosystems, simple but resilient, laid the foundation for the Triassic. Picture a young landscape, Lystrosaurus nibbling ferns, algae blooming in a quiet pool, a lizard darting under a starry sky. These ecological impacts, born from volcanic decline, heralded a new era. As you sink into sleep, let the image of a reborn world cradle you, its resilience a soothing whisper. Ocean reoxygenation. As we drift deeper into the great dying's aftermath, let your mind settle on the oceans, where silence gives way to the gentle pulse of life returning. 252 million years ago, the Permian-Triassic extinction left the seas barren, with 96% of marine species lost to acidification and anoxia. Yet, by 251 million years ago, the oceans began to breathe again. Microfossils in China's Meishan beds reveal algae blooms spreading, their green tendrils a sign of reoxygenation. Turkey's limestone shows microbial mats carpeting the seafloor, while Japan's sediments mark the return of small mollusks. The Paleontologic Ocean, once a graveyard, stirred with renewal, its waters clearing under a softening sky. Picture a shallow sea, green algae shimmering, a lone chlorea shell glinting in pale sunlight, waves lapping gently. This chapter explores the reoxygenation of the oceans, a pivotal step in ending the great dying. From algae proliferation to the rebirth of food webs, we'll uncover how the seas healed. Let these ancient waters cradle you, their quiet recovery a soothing path to sleep. Algae proliferation. The first whispers of recovery came from algae, the ocean's silent architects. As volcanic activity waned, carbon dioxide levels dropped, easing acidification, per 2025 geochemical studies. Microfossils in China's Meishan beds, dated to 251 million years ago, show blooms of cyanobacteria and green algae, their rapid growth fueled by nutrient-rich waters from volcanic ash. These blooms, preserved in Japan's Paleontologic sediments, absorbed CO2 and released oxygen, a critical step in reoxygenating the seas. In shallow bays, algae formed green films, as seen in Turkey's limestone deposits, creating habitats for early survivors. Their photosynthesis, documented in 2024 paleontological records, stabilized marine chemistry, reducing toxic hydrogen sulfide. Algae's resilience, thriving in harsh conditions, laid the foundation for recovery. Picture a barren sea, its surface shimmering with green, algae pulsing in gentle waves, the water alive with microscopic life. These blooms, though invisible to the eye, were mighty, rebuilding the ocean's breath. Fossils in Canada's Arctic shale show algae supporting small mollusks, a sign of life's return. As you relax, let the image of a green sea soothe you, its quiet growth a gentle nudge toward dreams. Oxygen return. With algae spreading, oxygen began to return to the oceans, reviving ecosystems crushed by anoxia. Sedimentary records from Japan, analyzed in 2024, show oxygen levels rising in shallow waters, marked by lighter shale layers free of sulfur. Volcanic decline, per Siberian core samples, reduced greenhouse gases, cooling seas and boosting oxygen solubility. Deep ocean currents, slowed by warming, resumed, as evidenced by sediment mixing in Oman's rocks. This oxygen return, gradual but steady, allowed small fish and mollusks to recolonize bays, their fossils appearing in Greenland's deposits. Foraminifera, tiny protists in China's Meishan beds, thrived in oxygenated waters, their shells piling up in layers. Picture a shallow bay, waves carrying oxygen, a fish darting through clear water, the seafloor stirring with life. This oxygen resurgence was a lifeline, breathing life into silent seas. As you drift, let the rhythm of ancient currents envelop you, their pulse a soothing embrace. Reef regeneration. The collapse of Permian reefs left oceans barren, but regeneration began with microbial mats. Turkey's limestone, studied in 2025, shows mats of cyanobacteria carpeting the seafloor, replacing coral-like structures lost to acidification. These mats, also found in Italy's dolomite fossils, trapped sediments, forming new reef-like systems. Small mollusks like chlorea, preserved in China's sediments, colonized these mats, their shells adding structure. Algae and microbes, per 2024 studies, stabilized calcium levels, enabling early calcite formations in Oman's rocks. These proto-reefs, though simple, supported diverse life, from foraminifera to tiny crustaceans. Picture a seafloor, green mats spreading, chlorea shells glinting, waves above shimmering with pale light, a new reef rising. This reef regeneration, slow but persistent, rebuilt marine habitats. As you rest, let the image of a growing reef guide you, its calm a path to sleep. Marine pioneers. Pioneering species led the ocean's revival. Chlorea, a small mollusk, dominated early Triassic seas, its fossils in Japan's sediments showing rapid reproduction per 2024 records. Foraminifera, found in Greenland shale, formed dense populations, stabilizing food webs. Small fish, preserved in Canada's Arctic deposits, adapted to low-oxygen niches, their streamlined bodies suited for shallow bays. Early cephalopods, like ammonoids in China's Meishan beds, emerged with simple shells, scavenging in recovering waters. These pioneers, small but resilient, filled empty niches, their diversity a spark of renewal. Picture a shallow sea, chlorea shells scattered, a fish darting among microbial mats, the water alive with quiet movement. These marine pioneers, though modest, reshaped the seas, their tenacity a promise of life. As you drift, let the image of a reviving ocean soothe you, its pulse a gentle lullaby. Food web recovery. The return of oxygen and pioneers rebuilt marine food webs. Algae and foraminifera, per Japan's microfossils, formed the base, feeding small mollusks like chlorea. Early fish, found in Oman's sediments, preyed on these mollusks, while ammonoids scavenged debris, their fossils in Turkey showing active hunting. Microbial mats, per 2025 studies, supported crustaceans, their remains in China's limestone marking new predator-prey links. These simple food webs, seen in Greenland's fossil layers, stabilized ecosystems, paving the way for complex marine life. Picture a vibrant bay, algae blooming, fish darting, ammonoids gliding, the sea pulsing with new connections. This food web recovery, born from oxygen's return, heralded the Triassic's marine diversity. As you sink into sleep, let the image of a reborn sea cradle you, its resilience a soothing whisper. Carbon sequestration. As we journey further into the Great Dying's recovery, let your mind drift to a world where the Earth begins to heal itself, drawing carbon from the air to cool its fevered landscapes. 252 million years ago, The Permian-Triassic extinction was fueled by volcanic carbon dioxide, warming the planet to near collapse. Yet, by 251 million years ago, natural processes began locking away this excess carbon. Geochemical studies from Siberia's rocks, analyzed in 2025, show silicate weathering absorbing CO2, while China's limestone records algae trapping carbon in oceans. These processes cooled the climate, allowing ferns to spread in Australia's soils and mollusks to thrive in Japan's seas. Picture a rocky plain, rain washing over weathered stones, a green fern sprouting, the air fresh with the scent of renewal. This chapter explores carbon sequestration, a silent force that helped end the Great Dying. From weathering rocks to reborn ecosystems, we'll uncover how the Earth found balance. Let these ancient processes cradle you, their quiet work a soothing path to sleep. Weathering processes. The Earth's recovery began with the slow, steady work of rock weathering. As Siberian traps volcanism waned, silicate rocks, exposed across Pangaea, reacted with rainwater and CO2, per 2025 geochemical studies. This process, seen in Siberia's basalt layers, formed carbonate minerals, locking carbon away for millennia. Acid rain, once destructive, now aided weathering, eroding rocks in Australia's Bowen Basin and depositing calcium in soils, as evidenced by 2024 sedimentary records. This chemical dance reduced atmospheric CO2, cooling the planet by several degrees, per isotopic data. Ferns, preserved in Brazil's shale, sprouted in these stabilized soils, their roots aiding further weathering. Picture a rocky hillside, rain trickling over basalt, faint green ferns emerging, the air cooling with each drop. Weathering was a quiet healer, drawing carbon from the skies to restore balance. As you relax, let the image of rain-washed rocks soothe you, their steady work a gentle nudge toward dreams. Carbon sinks. Carbon sinks, from oceans to soils, played a vital role in recovery. Algae blooms, preserved in China's Meishan microfossils, absorb CO2 through photosynthesis, locking it into marine sediments by 251 million years ago, per 2024 studies. On land, seed ferns and early conifers, found in Argentina's shale, sequestered carbon in their tissues, their roots stabilizing soils in India's deposits. Peat bogs, emerging in Brazil's coal beds, trapped carbon in organic layers, acting as natural sinks. Ocean carbonate formation, seen in Oman's limestone, further stored CO2, stabilizing marine chemistry. Picture a shallow sea, algae pulsing green, ferns spreading on a nearby shore, the air fresh with the scent of life. These sinks, both marine and terrestrial, drew down CO2, paving the way for recovery. As you drift, let the image of a green sea and sprouting ferns envelop you, their calm a soothing embrace. Climate cooling. As carbon was sequestered, the Earth's climate began to cool. The greenhouse effect, which raised temperatures 10 degrees Celsius, weakened as CO2 levels dropped, per 2025 isotopic data from Greenland's sediments. Weathering and algal uptake, evidenced in Siberia's rocks, reduced atmospheric CO2, stabilizing temperatures. Storms, once violent, calmed, with Australia's sedimentary layers showing reduced erosion. Coastal ecosystems, preserved in Japan's fossils, stabilized as sea levels steadied. Fern forests, found in Antarctica's soils, expanded in cooler conditions, their green canopies a sign of balance. Picture a barren plain, clouds parting, a cool breeze stirring ferns, the horizon softening under a pale sky. This cooling climate gave survivors space to thrive, a critical step in recovery. As you rest, let the image of a cooling world guide you. Its balance a path to sleep. Ecosystem rebound. With cooling climates, ecosystems began to rebound. Fossils in South Africa's Karoo Basin show Lystrosaurus populations growing, grazing on expanding fern forests, per 2024 paleobiology data. In oceans, microbial mats in Turkey's limestone supported mollusks like chlorea, rebuilding food webs. Seed ferns and conifers, preserved in Brazil's shale, stabilized soils, enabling small lizards to thrive, as seen in India's fossils. These ecosystems, simple but resilient, filled empty niches, their diversity a spark of renewal. Picture a young forest, Lystrosaurus nibbling ferns, a shallow sea alive with mollusks, the air fresh with growth. This rebound, driven by carbon sequestration, rebuilt life's foundations. As you drift, let the image of a reviving ecosystem soothe you, its growth a gentle lullaby. Long-term stabilization. Carbon sequestration ensured long-term stabilization, setting the stage for the Triassic. Geochemical records from China's limestone, studied in 2025, show sustained CO2 drawdown, maintaining cooler climates. Terrestrial carbon sinks, like peat bogs in Russia's deposits, locked carbon for millennia, while marine sediments in Oman's rocks preserved it in calcite. These processes, per 2024 studies, prevented climate swings, allowing ferns and conifers to spread across Pangaea, as seen in Argentina's fossils. Early archosaurs, found in India's red beds, thrived in stable ecosystems, heralding new diversity. Picture a stable landscape, fern forest stretching, a shallow sea shimmering, the sky clear under a starry night. This stabilization, born from carbon's quiet work, secured life's future. As you sink into sleep, let the image of a balanced world cradle you, its resilience a soothing whisper. Rise of new species. As we journey deeper into the aftermath of the Great Dying, let your mind drift to a world reborn, where new life rises from the ashes of catastrophe. 252 million years ago, the Permian-Triassic extinction left Earth's landscapes and oceans nearly empty, but by the early Triassic, new species emerged to fill the void. Fossils in Australia's Bowen Basin reveal early archosaurs, ancestors of dinosaurs, scuttling through fern forests. In China's marine sediments, ichthyosaurs swam in reviving seas. Conifers spread across Argentina's plains, their needles catching soft sunlight. These new species, born from resilience, reshaped a healing planet. Picture a young forest, an archosaur darting through ferns, a distant sea alive with gliding reptiles, the air fresh with possibility. This chapter explores the rise of new species, their adaptations, and the ecological shifts they sparked. Let these ancient pioneers guide you, their quiet emergence a soothing path to sleep. Archosaur emergence. The early Triassic saw the rise of archosaurs, ancestors of dinosaurs and crocodiles, filling empty terrestrial niches. Fossils in Australia's Bowen Basin, studied in 2024, reveal small, agile archosaurs like Proterosuchus, their slender limbs suited for sprinting across sparse plains. These reptiles, per paleontological records, had flexible metabolisms, allowing survival in fluctuating climates. In South Africa's Karoo Basin, their tracks show rapid movement, hunting insects and small synapsids. Unlike the bulky therapsids of the Permian, archosaurs were lightweight, their fossils in India's red beds indicating early diversification. Picture a sunlit plain, a proterosuchus darting through ferns, its scales glinting, the air warm with a cooling breeze. Archosaurs' adaptability made them pioneers, their rise a spark of the Triassic's diversity. As you relax, let the image of a scampering archosaur soothe you, its quiet steps a gentle nudge toward dreams. Marine reptiles. In the oceans, marine reptiles emerged, reclaiming the seas. Fossils in China's Meishan beds, dated to 251 million years ago, show early ichthyosaurs, their streamlined bodies gliding through shallow waters, per 2025 studies. These reptiles, with dolphin-like forms, evolved from land ancestors, their fossils in Japan's sediments revealing rapid adaptation to marine life. Small plesiosaurs, found in Greenland's shale, swam in oxygenated bays, preying on mollusks like chlorea. Their paddle-like limbs, preserved in Canada's deposits, enabled agile hunting. Picture a calm sea, an ichthyosaur gliding through green waves, its sleek form cutting the water, sunlight dancing above. These marine reptiles, swift and graceful, filled vacant niches, their presence a sign of recovery. As you drift, let the image of a gliding ichthyosaur envelop you, its motion a soothing embrace. Plant diversification. On land, plants diversified, rebuilding ecosystems. Conifers, with needle-like leaves, spread across Argentina's plains, their fossils in 2024 shale records showing drought resistance. Seed ferns, preserved in Australia's Bowen Basin, expanded with heat-tolerant spores, colonizing barren soils. Cycads, found in India's deposits, emerged with tough, waxy leaves, thriving in cooling climates. These plants, per 2025 botanical studies, stabilized soils, supporting herbivores like Lystrosaurus. Their seeds, scattered in Brazil's sedimentary layers, ensured rapid regrowth. Picture a young forest, conifers swaying, ferns carpeting the ground, a soft breeze carrying the scent of green. This plant diversification laid the foundation for terrestrial recovery, their growth a promise of life. As you rest, let the image of a spreading forest guide you, its calm a path to sleep. Ecological shifts. The rise of new species drove ecological shifts, reshaping the Triassic world. Archosaurs, per South Africa's fossils, became dominant predators, hunting insects and small reptiles, filling niches left by Permian-Triassics. In oceans, ichthyosaurs and plesiosaurs, seen in China's sediments, preyed on mollusks, rebuilding food webs. Conifers and ferns, preserved in Antarctica's soils, supported herbivores, enabling population growth. These shifts, per 2024 ecological studies, created stable ecosystems, with fossil tracks in Australia showing diverse interactions. Picture a vibrant plain, an archosaur stalking, ferns rustling, a distant sea alive with reptiles, the sky clear under stars. These ecological shifts, born from new species, heralded a new era. As you sink into sleep, let the image of a reborn world cradle you, its resilience a soothing whisper. Rebuilding ecosystems. As we journey deeper into the Triassic dawn, let your mind drift to a world knitting itself back together, where ecosystems rise from the scars of the Great Dying. 252 million years ago, the Permian-Triassic extinction left Earth's landscapes and oceans desolate, but by 251 million years ago, new ecosystems began to flourish. Fossils in South Africa's Karoo Basin show fern forests teeming with Lystrosaurus, while China's marine sediments reveal ichthyosaurs hunting in vibrant seas. Conifers spread across Australia's plains, their roots anchoring new food webs. These ecosystems, fragile but thriving, marked a new chapter for life. Picture a lush valley, ferns swaying, an archosaur stalking through shadows, a distant sea alive with gliding reptiles, the air warm with renewal. This chapter explores the rebuilding of ecosystems, from terrestrial recovery to marine revival, and the intricate connections that sustain them. Let these ancient landscapes guide you, their quiet growth a soothing path to sleep. Terrestrial recovery. The early Triassic saw terrestrial ecosystems reborn from barren plains. Fossils in South Africa's Karoo Basin, studied in 2024, show Lystrosaurus herds grazing on fern forests, their numbers swelling in stabilized soils. Seed ferns and early conifers, preserved in Australia's Bowen Basin, spread rapidly, their spores thriving in cooling climates. Per 2025 botanical records, small archosaurs, like Proterosuchus, found in India's red beds, hunted insects and small synapsids, their tracks indicating active ecosystems. Soil stabilization, evidenced by root fossils in Brazil's shale, prevented erosion, allowing plant communities to expand. These terrestrial systems, simple but robust, rebuilt food chains. Picture a sunlit plain, Lystrosaurus nibbling ferns, conifers casting soft shadows, a cool breeze stirring the air. This terrestrial recovery, driven by resilient plants and animals, laid the foundation for diverse ecosystems. As you relax, let the image of a growing forest soothe you, its quiet life a gentle nudge toward dreams. Marine ecosystem restoration. In the oceans, ecosystems revived as oxygen returned. China's Meishan beds, analyzed in 2025, show microbial mats supporting mollusks like chlorea, their shells piling up in vibrant bays. Early ichthyosaurs, preserved in Japan's sediments, hunted small fish, per 2024 paleontological records, forming new predator-prey links. Foraminifera and ammonoids, found in Greenland's shale, thrived in oxygenated waters, stabilizing food webs. Proto-reefs, seen in Turkey's limestone, grew from microbial mats, hosting crustaceans and small cephalopods. These marine ecosystems, per 2025 studies, marked a return to complexity. Picture a shallow sea, green mats pulsing, an ichthyosaur gliding through clear waves, sunlight shimmering above. This marine restoration, fueled by oxygen and pioneers, rebuilt the sea's vitality. As you drift, let the image of a thriving ocean envelop you, its pulse a soothing embrace. Predator-prey dynamics. New predator-prey dynamics shaped recovering ecosystems. On land, archosaurs like Proterosuchus, per South Africa's fossils, hunted small lizards and insects, their sharp teeth preserved in 2024 records. In oceans, ichthyosaurs and early plesiosaurs, found in Canada's shale, preyed on mollusks and fish, their fossils showing bite marks on chlorea shells. These dynamics, per 2025 ecological studies, stabilized populations, preventing overgrazing. Insects, like beetles and rushes deposits, supported small predators, their remains indicating diverse food chains. Picture a fern forest, an archosaur stalking a beetle, a distant sea where an ichthyosaur snaps at a fish, the air alive with movement. These dynamics, balancing life and death, strengthen ecosystems. As you rest, let the image of a lively hunt guide you, its rhythm a path to sleep. Plant-animal interactions. Plant-animal interactions fueled ecosystem growth. Ferns and conifers, preserved in Argentina's shale, provided food for Lystrosaurus, their fossils showing bite marks, per 2024 studies. Insects, like pollinators in India's deposits, aided plant reproduction, their remains found with pollen grains. In oceans, algae blooms, seen in Japan's microfossils, fed mollusks like chlorea, supporting fish populations. These interactions, per 2025 ecological data, created feedback loops, stabilizing ecosystems. Root systems in Brazil's soils supported burrowing synapsids, their tunnels preserving plant fragments. Picture a lush plain, Lystrosaurus grazing ferns, beetles buzzing, a sea where algae feed mollusks, the world humming with life. These interactions, binding plants and animals, wove ecosystems together. As you drift, let the image of a connected world soothe you, its harmony a gentle lullaby. Global ecosystem expansion. Ecosystems expanded globally, uniting land and sea. Fossils in Antarctica's soils show fern forests spreading, supporting Lystrosaurus herds, per 2024 records. In oceans, proto-reefs in Oman's limestone hosted diverse mollusks and fish, their fossils indicating thriving communities. Archosaurs, found in Russia's deposits, colonized new regions, their tracks showing migration. These ecosystems, per 2025 studies, linked across Pangaea, creating stable networks. Conifers in Australia's plains and ichthyosaurs in China's seas marked a global recovery. Picture a vast landscape, fern forests stretching, a sea teeming with reptiles, the sky clear under stars. This global expansion, uniting ecosystems, heralded the Triassic's diversity. As you sink into sleep, let the image of a reborn world cradle you, its resilience a soothing whisper. Climatic shifts. As we journey deeper into the Triassic recovery, let your mind drift to a world where the Earth's climate softens, its harsh extremes giving way to gentle balance. 252 million years ago, the Permian-Triassic extinction scorched the planet with volcanic heat, but by 251 million years ago, climatic shifts brought renewal. Isotopic data from Greenland's sediments, studied in 2025, show cooling temperatures, while Australia's fossil soils reveal steady rains nurturing fern forests. In China's marine sediments, clearer skies supported thriving mollusks, their shells glinting in reviving seas. These shifts, subtle but profound, cradled life's return. Picture a cooling plain, raindrops pattering on ferns, a soft breeze under a clearing sky, the world breathing anew. This chapter explores the climatic shifts that fostered recovery, from cooling temperatures to new seasonal patterns. Let these ancient changes guide you, their quiet harmony a soothing path to sleep. Temperature stabilization. As volcanic activity from the Siberian traps waned, Earth's temperatures began to stabilize. Isotopic data from Greenland's sediments, analyzed in 2025, show a drop of several degrees Celsius by 251 million years ago, easing the greenhouse crisis that raised global temperatures by 10 degrees. Carbon sequestration, per Siberia's weathered basalt, absorbs CO2, cooling the planet. Fossils in Australia's Bowen Basin reveal fern forests expanding in milder climates, their fronds thriving in stable conditions. In oceans, cooler waters, seen in Japan's shale, supported mollusks like Karoo, their shells marking oxygenated bays. These changes, per 2024 studies, allowed ecosystems to flourish. Picture a sunlit plain, ferns swaying in a cool breeze, the air soft with the scent of damp earth. This temperature stabilization, a gentle reprieve, gave life room to grow. As you relax, let the image of a cooling world soothe you. Its calm a gentle nudge toward dreams. Rainfall patterns. New rainfall patterns reshaped the Triassic landscape. Sedimentary records from Brazil's shale, studied in 2024, show consistent rains replacing the erratic storms of the Permian crisis. These rains, driven by cooling climates, nourished fern forests, as seen in Antarctica's fossil soils. In Australia's Bowen Basin, root systems indicate wetter conditions, stabilizing soils against erosion. Coastal regions, per Oman's sedimentary layers, saw steady freshwater input, supporting algae and mollusks. These patterns, per 2025 hydrological models, fostered plant growth and water availability. Picture a fern valley, raindrops glistening on green fronds, a gentle stream flowing, the air fresh with moisture. These rainfall patterns, nurturing and reliable, rebuilt terrestrial ecosystems. As you drift, let the sound of ancient rains envelop you, their rhythm a soothing embrace. Atmospheric recovery. The atmosphere, once choked with volcanic gases, began to clear. Geochemical studies from China's limestone, dated 2025, show declining CO2 and sulfur levels as weathering and algae absorbed pollutants. Clearer skies, per Greenland's sediment records, allowed sunlight to reach plants, boosting photosynthesis in Australia's fern forests. Reduced acid rain, seen in Brazil's shale, preserved soils, enabling conifer growth. In oceans, cleaner air supported microbial mats, per Turkey's limestone fossils, fostering marine recovery. This atmospheric shift, per 2024 studies, restored ecological balance. Picture a clear sky, sunlight filtering through, ferns glowing green, a distant sea shimmering. This atmospheric recovery, a breath of fresh air, revived life's prospects. As you rest, let the image of a clearing sky guide you, its calm a path to sleep. Seasonal cycles. Seasonal cycles emerged, stabilizing ecosystems. Fossil soils and Russia's deposits, studied in 2025, show growth rings in early conifers, indicating predictable wet and dry seasons. These cycles, per 2024 paleoclimate models, supported fern reproduction, with spores thriving in seasonal rains, as seen in India's fossils. In oceans, seasonal upwelling, evidenced in Japan's sediments, brought nutrients to mollusks and fish, boosting populations. Archosaurs, per South Africa's tracks, adapted to seasonal food availability, their fossils showing migratory patterns. Picture a forest, ferns lush in rainy season, an archosaur foraging under a starry dry season sky. These seasonal cycles, steady and nurturing, anchored life's recovery. As you drift, let the rhythm of ancient seasons soothe you, their balance a gentle lullaby. Ecosystem adaptation. Ecosystems adapted to these climatic shifts, thriving in new conditions. Fossils in South Africa's Karoo Basin show Lystrosaurus adjusting to cooler temperatures, grazing on expanding ferns. In oceans, ichthyosaurs, per China's sediments, exploited seasonal nutrient blooms, their fossils indicating robust populations. Conifers and ferns, preserved in Argentina's shale, adapted to seasonal rains, their seeds spreading widely. Small predators, like archosaurs in Australia's fossils, honed hunting strategies for seasonal prey, per 2025 studies. These adaptations, global in scope, rebuilt vibrant ecosystems. Picture a thriving plain, ferns swaying, an ichthyosaur gliding in a distant sea, the world alive under a clear sky. These adaptations, harmonizing with climate, ensured life's resurgence. As you sink into sleep, let the image of a thriving world cradle you, its resilience a soothing whisper. Biodiversity surge. As we venture deeper into the Triassic recovery, let your mind drift to a world bursting with new life, where the scars of the great dying give way to a vibrant surge of biodiversity. 252 million years ago, the Permian-Triassic extinction erased 90% of life, but by 250 million years ago, Earth pulsed with renewal. Fossils in South Africa's Karoo Basin reveal archosaurs diversifying, their forms evolving into early dinosaurs. China's marine sediments show ichthyosaurs and plesiosaurs thriving in vibrant seas. Australia's fossil soils bloom with conifers and ferns, knitting ecosystems together. This biodiversity surge reshaped the planet, a testament to life's resilience. Picture a lush valley, an archosaur darting through ferns, a sea alive with gliding reptiles, the air warm with the scent of growth. This chapter explores the biodiversity surge, a pivotal moment in the Triasic's dawn. From rapid species diversification to global ecosystem connectivity, let these ancient landscapes guide you, their thriving energy a soothing path to sleep. Rapid species diversification. The early Triassic witnessed a rapid diversification of species, filling the void left by the Great Dying. Fossils in South Africa's Karoo Basin, studied in 2025, reveal archosaurs like Erythrosuchus evolving into varied forms, their skeletal structures, per 2024 paleontological records, showing adaptations for predation and mobility. Early dinosaurs, such as Eoraptor, found in Argentina's shale, emerged with lightweight bodies, marking the start of a dominant lineage. In oceans, ammonoids diversified rapidly, their spiral shells in China's Meishan beds indicating high reproductive rates, per 2025 studies. Terrestrial insects, like beetles in Russia's deposits, evolved new feeding strategies, supporting predators. Plants, including seed ferns and cycads in Australia's Bowen Basin, developed diverse reproductive methods, per 2024 botanical data, colonizing varied climates. This surge, driven by empty niches and stable climates, per 2025 ecological models, allowed life to experiment with new forms. Genetic studies, reconstructed from fossil proteins in 2024, show accelerated mutation rates, fueling diversity. On land, small synapsids like Thrinaxodon, preserved in Brazil's red beds, adapted to nocturnal niches, while early turtles appeared in Germany's fossils, their shells a novel defense. Picture a sunlit plain, an Eoraptor sprinting, ferns swaying, a beetle buzzing under a conifer's shade, the world alive with new forms. This rapid diversification, a burst of evolutionary creativity, rebuilt life's tapestry. As you relax, let the image of a thriving plain soothe you, its diversity a gentle nudge toward dreams. Expansion of ecological niches. The biodiversity surge filled ecological niches left vacant by the extinction. On land, archosaurs like Proterosuchus, per South Africa's 2024 fossils, occupied predator roles, their sharp teeth suited for hunting small reptiles. Herbivores like Lystrosaurus, still dominant in Antarctica's deposits, grazed fern forests, their numbers stabilizing ecosystems, per paleobiology data. In oceans, ichthyosaurs, found in Japan's sediments, evolved into apex predators, their streamlined bodies ideal for chasing fish, per 2025 studies. Mollusks like Chlorea, preserved in China's limestone, colonized seafloors, creating niches for scavengers. Plants, such as conifers in Argentina's shale, filled canopy rolls, their seeds spreading widely, per 2024 botanical records. Insects, like dragonfly ancestors in India's deposits, exploited new food sources, supporting small predators. These niches, per 2025 ecological models, fostered interdependence, with fossilized food webs in Brazil's shale showing complex interactions. Coastal ecosystems, evidenced in Oman's sediments, supported amphibians, their fossils indicating semi-aquatic niches. This expansion, driven by climatic stability and resource availability, created robust ecosystems. Picture a fern forest, Lystrosaurus grazing, an ichthyosaur gliding in a distant sea, the air humming with life. This niche expansion, weaving life together, strengthened the Triassic's ecosystems. As you drift, let the image of a connected world envelop you, its harmony a soothing embrace. Marine recovery. Marine ecosystems roared back with diverse life forms. Fossils in China's Meishan beds, dated to 250 million years ago, show ichthyosaurs diversifying, their varied sizes, per 2024 records, indicating niche specialization. Plesiosaurs, found in Greenland's shale, developed long necks for hunting in shallow bays, their fossils showing bite marks on mollusks. Ammonoids and nautiloids, preserved in Japan's sediments, exploded in variety, their buoyancy aiding survival, per 2025 studies. Proto-reefs, seen in Turkey's limestone, grew from microbial mats, hosting crustaceans and small fish, per paleontological data. Nutrient upwelling, evidenced in Canada's deposits, fueled algae blooms, supporting food webs, per 2024 geochemical models. Early corals, found in Oman's rocks, began forming reef frameworks, a sign of recovery. Fish species, like coelacanth ancestors in South Africa's marine fossils, adapted to deeper waters, their robust fins suited for survival. These marine systems, interconnected by currents, rebuilt complex ecosystems. Picture a vibrant sea, an ichthyosaur darting, ammonoids floating, coral-like structures glowing under pale waves. This marine recovery, pulsing with life, restored the ocean's vitality. As you rest, let the image of a thriving sea guide you, its rhythm a path to sleep. Terrestrial recovery. Terrestrial ecosystems flourished with new species and interactions. Conifer forests, preserved in Australia's Bowen Basin, spread across Pangaea, their needle-like leaves resisting drought, per 2024 botanical studies. Ferns and cycads, found in India's deposits, colonized riverbanks, their spores thriving in seasonal rains, per 2025 data. Archosaurs, like Erythrosuchus, dominated as predators, their fossils in South Africa's Karoo Basin showing powerful builds. Early dinosaurs, such as Eoraptor, per Argentina's shale, were agile omnivores, filling versatile niches. Lystrosaurus, still prevalent in Antarctica's fossils, supported food webs, grazing vast fern plains. Insects, like beetles and early dragonflies in Russia's deposits, pollinated plants, creating symbiotic relationships per 2024 studies. Fossil tracks in Brazil's red beds show migratory patterns, indicating resource abundance. Small synapsids, like Thrinaxodon, adapted to burrowing, their fossils showing nocturnal habits. Picture a lush forest, an archosaur stalking, ferns rustling, a dragonfly hovering over a stream. This terrestrial recovery, vibrant and expansive, rebuilt life's foundation. As you drift, let the image of a thriving forest soothe you, its energy a gentle lullaby. Global ecosystem connectivity. Ecosystems became globally connected, uniting land and sea in a web of life. Fossil records in South Africa's Karoo Basin show archosaurs migrating across Pangaea, their tracks linking fern forests per 2025 studies. In oceans, ichthyosaurs and plesiosaurs, preserved in China's sediments, followed nutrient-rich currents, connecting coastal ecosystems. Conifers and ferns, found in Australia's and Argentina's deposits, spread seeds via wind and animals, creating uniform forests per 2024 botanical data. Marine proto-reefs in Oman's limestone supported fish that fed terrestrial predators per paleontological records, bridging ecosystems. Insects, like pollinators in India's fossils, facilitated plant dispersal, linking terrestrial food webs. Seasonal migrations, evidenced by fossil tracks in Russia, connected distant habitats. These connections, per 2025 ecological models, ensured resilience, with carbon cycles stabilizing climates, per Greenland's isotopic data. Picture a global landscape, fern forests stretching, ichthyosaurs gliding in a distant sea, the world united under a starry sky. This global connectivity, weaving ecosystems together, secured the Triassic's future. As you sink into sleep, let the image of a united world cradle you, its harmony a soothing whisper. Ecological stabilization. As we journey deeper into the Triassic recovery, let your mind drift to a world finding its balance, where ecosystems settle into harmony after the chaos of the Great Dying. 252 million years ago, the Permian-Triassic extinction left Earth's landscapes and oceans nearly barren, but by 250 million years ago, life had woven itself into stable networks. Fossils in South Africa's Karoo Basin show archosaurs like Erythrosuchus hunting in balanced food webs, while China's marine sediments reveal ichthyosaurs thriving in stable seas. Australia's fossil soils, rich with conifer roots, anchor flourishing fern forests. These ecosystems, steady and resilient, marked a new era. Picture a tranquil valley, ferns swaying under a gentle breeze, an archosaur stalking quietly, a distant sea shimmering with life, the air warm with stability. This chapter explores the ecological stabilization that secured the Triassic's recovery, from balanced food webs to resilient ecosystems. Let these ancient harmonies guide you, their quiet strength a soothing path to sleep. Balanced food webs. The early Triassic saw the emergence of balanced food webs, anchoring ecosystems. In South Africa's Karoo Basin, fossils dated to 250 million years ago, per 2025 studies, show Lystrosaurus grazing vast fern plains, supporting predators like Erythrosuchus, whose sharp teeth indicate efficient hunting. Insects, such as beetles preserved in Russia's deposits, fed small archosaurs, their remains showing pollination roles. Per 2024 ecological data. In oceans, China's Meishan beds reveal ichthyosaurs preying on fish and mollusks like chlorea, their bite marks preserved in shells. Ammonoids, found in Japan's sediments, scavenge debris, stabilizing marine food chains. Per 2025 paleontological records. These webs, balanced by resource availability, prevented overgrazing, as seen in Antarctica's fossil soils where plant remains show sustainable herbivory. Terrestrial predators, like early dinosaurs in Argentina's shale, hunted small prey, maintaining population control. Coastal ecosystems, per Oman's sedimentary layers, linked land and sea, with amphibians feeding on marine crustaceans. This balance, per 2024 ecological models, ensured ecosystem stability across Pangaea. Picture a vibrant plain, Lystrosaurus nibbling ferns, and Erythrosuchus stalking, a distant sea where ichthyosaurs glide, the world pulsing with equilibrium. These balanced food webs, weaving life together, secured the Triassic's ecosystems. As you relax, let the image of a harmonious plain soothe you, its balance a gentle nudge toward dreams. Climate consistency. Consistent climates supported ecological stability, fostering life's resurgence. Isotopic data from Greenland's sediments, analyzed in 2025, show stable temperatures by 250 million years ago, with fluctuations reduced to within a few degrees, per paleoclimate models. Carbon sequestration, evidenced in Siberia's weathered basalt, maintained low CO2 levels, cooling the planet. Australia's fossil soils reveal consistent seasonal rains, nourishing fern forests, per 2024 hydrological studies. In oceans, stable currents, seen in Japan's sedimentary layers, distributed nutrients, supporting ichthyosaur and mollusk populations. Reduced storm intensity, per Brazil's shale records, protected coastal ecosystems, allowing proto-reefs in Oman's limestone to thrive. These stable climates, per 2025 studies, enabled plants like conifers in Argentina's deposits to spread uniformly, their growth rings showing predictable seasons. Terrestrial animals, like archosaurs in South Africa's fossils, adapted to consistent resources, their tracks indicating regular migrations. Picture a calm valley, ferns glowing under steady sunlight, a gentle rain falling, the air soft with stability. This climate consistency, a steady rhythm, nurtured thriving ecosystems. As you drift, let the image of a balanced world envelop you, its calm a soothing embrace. Soil and sediment stability. Stable soils and sediments anchored ecosystems, preventing erosion and supporting life. Fossil soils in Australia's Bowen Basin, studied in 2024, show conifer and fern roots binding earth, reducing runoff, per sedimentological data. In South Africa's Karoo Basin, Lystrosaurus burrows, preserved in 2025 fossils, stabilized soils, creating habitats for insects. In oceans, microbial mats in Turkey's limestone, per 2024 records, trapped sediments, forming proto-reefs that supported mollusks like chlorea. Riverbanks, evidenced in Brazil's shale, were reinforced by cycad roots, maintaining clear waterways for amphibians. These stable substrates, per 2025 geological studies, allowed ecosystems to expand without disruption. In coastal zones, Oman's sedimentary layers show reduced erosion, preserving habitats for fish and crustaceans. Terrestrial plants, like seed ferns in India's deposits, spread rapidly, their roots locking soils in place. This stability, per 2024 models, supported diverse food webs. Picture a lush plain, fern roots gripping soil, a clear stream flowing, a distant reef steady under waves. This soil and sediment stability, grounding ecosystems, ensured their endurance. As you rest, Let the image of a rooted landscape guide you, its strength a path to sleep. Species interactions. Complex species interactions strengthen ecosystems, fostering resilience. In South Africa's Karoo Basin, 2025 fossils show Erythrosuchus preying on Lystrosaurus, their interactions balancing herbivore populations. Insects, like dragonfly ancestors in Russia's deposits, pollinated ferns, per 2024 botanical data, supporting plant reproduction. In oceans, ichthyosaurs, preserved in China's Meishan beds, hunted fish, while ammonoids scavenged, creating dynamic food webs, per paleontological records. Coastal amphibians, found in Oman's fossils, link terrestrial and marine systems, feeding on crustaceans. Plants like conifers in Argentina's shale provided shade, fostering microhabitats for small reptiles, per 2025 studies. These interactions, evidenced by fossilized bite marks and pollen in Brazil's deposits, created feedback loops, stabilizing ecosystems. Early dinosaurs, like Eoraptor in Argentina's fossils, foraged opportunistically, adapting to varied prey. Picture a vibrant forest, an archosaur chasing a beetle, ferns swaying, a sea where ichthyosaurs hunt, the world alive with connections. These species interactions, binding life together, wove a resilient web. As you drift, let the image of a connected ecosystem soothe you, its harmony a gentle lullaby. Long-term ecosystem resilience. Ecosystems achieved long-term resilience, securing the Triassic's future. Fossils in South Africa's Karoo Basin, per 2025 studies, show diverse archosaur populations, their adaptability ensuring survival through minor climate shifts. In oceans, proto-reefs in Turkey's limestone, per 2024 records, supported stable mollusk and fish communities, resisting disruptions. Conifer forests, preserved in Australia's deposits, spread globally, their seeds ensuring regrowth, per botanical data. Carbon cycles, stabilized by weathering in Siberia's basalt, maintained climate balance, per 2025 isotopic studies. Migratory patterns, seen in Russia's fossil tracks, linked ecosystems across Pangaea, enhancing resilience. Marine food webs, per China's sediments, remained robust, with ichthyosaurs and ammonoids thriving. These systems, per 2024 ecological models, withstood environmental stresses, ensuring longevity. Picture a global landscape, fern forests stretching, ichthyosaurs gliding in a stable sea, the world united under a starry sky. This long-term resilience, a testament to life's strength, secured the Triassic's legacy. As you sink into sleep, let the image of a resilient world cradle you, its harmony a soothing whisper. Dawn of the Triassic. As we near the end of our journey through the Great Dying's recovery, let your mind drift to a world reborn, where the Triassic dawns in vibrant splendor. 252 million years ago, the Permian-Triassic extinction left Earth nearly lifeless, but by 250 million years ago, the planet pulsed with new energy. Fossils in South Africa's Karoo Basin show archosaurs prowling lush fern forests, while China's marine sediments reveal ichthyosaurs gliding through thriving seas. Conifers tower in Australia's plains, their seeds carried by gentle winds. This was the dawn of the Triassic, a time of flourishing life. Picture a vibrant valley, ferns swaying, an archosaur stalking, a distant sea alive with reptiles, the air warm with the scent of growth. This chapter explores the dawn of the Triassic, where ecosystems thrived and new species rose to dominance. Let these ancient landscapes guide you, their quiet vitality a soothing path to sleep. New ecosystem flourishing. The early Triassic saw ecosystems flourish across Pangaea, reborn from desolation. Fossils in South Africa's Karoo Basin, studied in 2025, show fern forests expanding, their fronds carpeting stable soils. Conifers, preserved in Australia's Bowen Basin, formed dense groves, their roots anchoring ecosystems, per 2024 botanical records. In oceans, microbial mats in Turkey's limestone supported thriving mollusks like chlorea, creating proto-reefs, per paleontological data. These ecosystems, interconnected by stable climates, fostered biodiversity. Small streams, evidenced in Brazil's shale, watered fern valleys, supporting Lystrosaurus herds. Insects, like beetles in Russia's deposits, buzzed through forests, aiding pollination. This flourishing, per 2025 ecological studies, marked a new balance. Picture a lush plain, ferns glowing under sunlight, a stream trickling, the air humming with life. These ecosystems, resilient and interconnected, rebuilt the world's vitality. As you relax, let the image of a thriving forest soothe you, its quiet growth a gentle nudge toward dreams. Rise of dominant species. New dominant species emerged, shaping the Triassic landscape. Archosaurs, like Erythrosuchus, found in South Africa's fossils, became apex predators, their robust jaws, per 2024 records, hunting small synapsids. Lystrosaurus, still abundant in Antarctica's deposits, grazed vast fern plains, its numbers stabilizing ecosystems. In oceans, ichthyosaurs, preserved in China's Meishan beds, dominated as swift predators, their streamlined bodies suited for hunting fish. Early dinosaurs, like Eoraptor, appeared in Argentina's shale, their small, agile forms, per 2025 studies, marking the start of a lineage. These species filled key niches, driving ecological balance. Picture a sunlit valley, an Erythrosuchus stalking, Lystrosaurus grazing, a distant sea with ichthyosaurs gliding. These dominant species, bold and adaptable, define the Triassic's resurgence. As you drift, let the image of a powerful archosaur envelop you, its presence a soothing embrace. Marine life diversification. The oceans teemed with new life as marine species diversified. Fossils in Japan's sediments, dated to 250 million years ago, show ichthyosaurs evolving varied forms, per 2024 paleontological records. Early plesiosaurs, found in Greenland's shale, swam with paddle-like limbs, preying on ammonoids. Mollusks like chlorea, preserved in China's limestone, formed dense beds, supporting fish populations. Coral-like structures, seen in Oman's reefs, began to return, hosting crustaceans, per 2025 studies. Nutrient-rich waters, driven by upwelling in Canada's deposits, fueled this diversity. Picture a vibrant sea, ichthyosaurs darting, mollusks glinting on the seafloor, waves shimmering under pale sunlight. This marine diversification, thriving in renewed seas, rebuilt oceanic ecosystems. As you rest, let the image of a lively ocean guide you, its pulse a path to sleep. Terrestrial expansion. Terrestrial ecosystems expanded across Pangaea, colonizing once barren lands. Conifer forests, preserved in Argentina's shale, spread into new regions, their seeds carried by winds, per 2024 botanical data. Ferns, found in India's deposits, colonized riverbanks, their roots stabilizing soils. Archosaurs, like Proterosuchus, migrated widely, their tracks in Australia's fossils showing long journeys. Early dinosaurs, per Russia's red beds, explored open plains, their small size aiding survival. These expansions, per 2025 ecological studies, connected ecosystems globally. Picture a vast plain, conifers towering, an archosaur sprinting, ferns lining a gentle river. This terrestrial expansion, uniting landscapes, fueled the Triassic's growth. As you drift, let the image of a spreading forest soothe you, its reach a gentle lullaby. Stable food webs. Stable food webs emerged, anchoring the Triassic's ecosystems. On land, Lystrosaurus grazed ferns, supporting predators like Erythrosuchus per South Africa's fossils. Insects, found in Brazil's deposits, fed small archosaurs, their remains showing pollination roles. In oceans, mollusks and fish, preserved in China's sediments, sustained ichthyosaurs and plesiosaurs, per 2024 records. Proto-reefs in Oman's limestone supported complex chains, with ammonoids scavenging debris. These webs, per 2025 ecological models, balance populations, ensuring resilience. Picture a vibrant ecosystem, Lystrosaurus grazing, ichthyosaurs hunting, ferns swaying under a starry sky. These stable food webs, weaving life together, secured the Triassic's future. As you sink into sleep, let the image of a thriving world cradle you, its harmony a soothing whisper. Legacy of recovery. As we reach the final chapter of our journey through the Great Dying's recovery, let your mind drift to a world transformed, where the Triassic's legacy endures in vibrant ecosystems and evolutionary triumphs. 252 million years ago, the Permian-Triassic extinction nearly silenced life, but by 250 million years ago, Earth thrived anew. Fossils in South Africa's Karoo Basin reveal early dinosaurs like Eoraptor roaming stable fern forests, while China's marine sediments show ichthyosaurs gliding through resilient seas. Australia's fossil soils, thick with conifer roots, anchor a world reborn. This legacy, built on resilience, shaped life's future. Picture a lush valley, an Eoraptor darting through ferns, a distant sea alive with reptiles, the air warm with the scent of eternity. This chapter explores the legacy of the Triassic recovery, from enduring ecosystems to lessons for our planet today. Let these ancient triumphs guide you, their quiet resilience a soothing path to sleep. Enduring ecosystems. The Triassic recovery forged ecosystems that endured for millions of years. Fossils in South Africa's Karoo Basin, studied in 2025, show fern forests and conifer groves thriving, their roots stabilizing soils, per 2024 sedimentological records. These terrestrial ecosystems, home to Lystrosaurus and early dinosaurs like Eoraptor, maintain balance through diverse food webs, per paleontological data. In oceans, proto-reefs in Turkey's limestone, dated to 250 million years ago, supported mollusks like chlorea and fish, forming resilient marine habitats, per 2025 studies. Coastal systems, seen in Oman's sediments, linked land and sea, with amphibians feeding on crustaceans. Stable climates, per Greenland's isotopic data, ensured these ecosystems resisted minor disruptions. Conifers, preserved in Argentina's shale, spread globally, their seeds carried by winds, per 2024 botanical records. Insects, like beetles in Russia's deposits, pollinated plants, reinforcing ecosystem stability. These enduring systems, per 2025 ecological models, supported life through the Triassic's challenges. Picture a vibrant plain, ferns swaying, an Eoraptor foraging, a distant reef thriving under gentle waves, the world steady and alive. These enduring ecosystems, rooted in recovery, shaped a lasting world. As you relax, let the image of a thriving forest soothe you, its stability a gentle nudge toward dreams. Evolutionary foundations. The recovery laid evolutionary foundations for modern life. Fossils in Argentina's shale, per 2025 studies, show early dinosaurs like Eoraptor, their lightweight bodies paving the way for Jurassic giants. Archosaurs, like Erythrosuchus in South Africa's Karoo Basin, evolved robust forms, per 2024 paleontological records, leading to crocodiles and birds. In oceans, ichthyosaurs, preserved in China's Meishan beds, developed streamlined bodies, influencing later marine reptiles. Ammonoids, found in Japan's sediments, diversified rapidly, their buoyancy systems, per 2025 data, inspiring cephalopod evolution. Terrestrial plants, like conifers in Australia's deposits, developed seed dispersal, shaping modern forests, per 2024 botanical studies. Small synapsids, like Thrinaxodon in Brazil's fossils, evolved mammalian traits, such as nocturnal vision. These foundations, per 2025 genetic reconstructions, set the stage for biodiversity surges. Insects, like dragonfly ancestors in India's deposits, adapted to new niches, supporting food webs. Picture a sunlit plain, an eoraptor sprinting, conifers towering, a sea where ichthyosaurs glide, the seeds of evolution sprouting. These evolutionary foundations, born from recovery, shaped life's future. As you drift, let the image of an evolving world envelop you, its promise a soothing embrace. Global biogeographic patterns. The recovery established global biogeographic patterns, uniting ecosystems across Pangaea. Fossils in South Africa's Karoo Basin show archosaurs migrating, their tracks, per 2025 studies, linking fern forests across continents. In oceans, ichthyosaurs and plesiosaurs, preserved in China's sediments, followed currents, connecting coastal habitats, per 2024 records. Conifers and ferns, found in Australia's and Argentina's deposits, spread uniformly, their seeds creating consistent flora, per botanical data. Marine proto-reefs in Oman's limestone supported fish that fed terrestrial predators, per paleontological studies, bridging ecosystems. Insects, like pollinators in Russia's fossils, facilitated plant dispersal, linking terrestrial zones. Migratory patterns, seen in Brazil's fossil tracks, connected distant habitats, per 2025 ecological models. Stable climates, per Greenland's isotopic data, enabled these patterns, ensuring uniform ecosystems. Coastal amphibians, in Oman's sediments, moved between land and sea, reinforcing connectivity. Picture a global landscape, fern forests stretching, ichthyosaurs swimming in a distant sea, the world united under a starry sky. These biogeographic patterns, weaving ecosystems together, created a cohesive world. As you rest, let the image of a united planet guide you, its harmony a path to sleep. Resilience to future stressors. Triassic ecosystems developed resilience to future stressors, ensuring longevity. Fossils in South Africa's Karoo Basin, per 2025 studies, show archosaurs like Erythrosuchus adapting to minor climate shifts, their robust forms surviving temperature fluctuations. In oceans, proto-reefs in Turkey's limestone, per 2024 records, withstood nutrient fluctuations, supporting stable mollusk populations. Conifers, preserved in Australia's deposits, resisted drought, their needle-like leaves conserving water, per botanical data. Carbon cycles, stabilized by weathering in Siberia's basalt, maintained climate balance, per 2025 isotopic studies. Food webs, per China's marine sediments, balanced predator-prey dynamics, with ichthyosaurs and ammonoids thriving. Migratory patterns, seen in Russia's fossil tracks, allowed species to evade local stressors. These adaptations, per 2024 ecological models, enabled ecosystems to endure volcanic pulses and sea level changes. Picture a resilient plain, ferns swaying through a storm, an ichthyosaur gliding in a stable sea, the world steadfast under clouds. This resilience, forged in recovery, secured ecosystems against challenges. As you drift, let the image of a steadfast world soothe you, its strength a gentle lullaby. Lessons for modern Earth. The Triassic recovery offers lessons for our modern Earth, facing climate challenges. The Great Dying, per 2025 studies, shows how carbon spikes, like those in Siberia's basalt, disrupted ecosystems, a warning for today's emissions. Carbon sequestration, seen in Australia's fossil soils, stabilized climates, suggesting reforestation and soil management as modern solutions. Diverse food webs, per South Africa's fossils, ensured resilience, a model for protecting biodiversity today. Marine recovery, evidenced in China's sediments, highlights the importance of ocean health, urging protection of reefs and fisheries. Global connectivity, per 2024 biogeographic data, shows ecosystems thrive when linked, a lesson for preserving migration corridors. Resilience to stressors, seen in Turkey's proto-reefs, inspires adaptive conservation strategies. The Triassic's recovery, per 2025 ecological models, teaches that life can rebound with time and balance. Picture a Triassic world, ferns thriving, ichthyosaurs swimming, a starry sky whispering hope for our planet. These lessons, drawn from ancient resilience, guide our path forward. As you sink into sleep, let the image of a reborn Earth cradle you, its wisdom a soothing whisper. Reflections on a Reborn Earth. As we close our journey through the great dying and its remarkable recovery, let your mind drift to a world that rose from near oblivion, its landscapes and seas now teeming with life. 252 million years ago, the Permian-Triassic extinction silenced 90% of Earth's species, but by 250 million years ago, a new world emerged. Fossils in South Africa's Karoo Basin whisper of early dinosaurs like Eoraptor, scampering through fern forests. China's marine sediments sing of ichthyosaurs gliding in vibrant seas. Australia's fossil soils, rich with conifer roots, cradle ecosystems that endured. This is the legacy of a planet reborn, a story of resilience and hope. Picture a serene valley, ferns swaying under a starry sky, an ichthyosaur gliding in a distant sea, the air warm with the breath of renewal. This call to dream, rooted in ancient resilience, guides us forward. As you sink into sleep, let the image of a reborn Earth cradle you, its hope a soothing whisper. Thanks for watching. Good night.